Hi everyone, today I brought a very nice question from the topic of vertical circular motion in the chapter work energy power. The question is something like this. We have two cases where in one case we have a string which is fixed at one end and on the other end a body is connected whose mass is m. You can think of this body as the bob of a pendulum, and this string's mass is negligible compared to the mass of the bob. And in the second case, we have replaced the string by a rod. Now, you all know that if I give this some velocity, it will try to go this way, right? And if the velocity given is very less, it will go somewhat here, stop. Why it will stop? Because its kinetic energy will convert into potential energy. So if you give very less kinetic energy, then it will stop somewhere here and then it will come back. So it will simply perform oscillation. Same thing for this bob, right? But if I give it very high velocity, then you know it is possible that this bob will complete a vertical circle. Similarly here, if you give very high velocity, it is possible to complete a vertical circle. We need to find the minimum velocity that should be given to the bob so that it can complete the circle. So we need to find the minimum velocity to complete the vertical loop. Okay. Try to observe this carefully. Think of this as a string and this is the bob. So I'm going to give it a small speed at the bottom and see what happens when the speed given is very small. So it just performs oscillation, right? It goes up to here, stops and comes back. Now let me give it quite a high speed at the bottom. See what happens. So you can see it successfully completes the loop if I give it high speed. Now, I'll try to give it a speed at which you will see that this bob, in this case my son's identity card, it will reach somewhere here, and instead of completing the circle, you will see that the string will become loose somewhere here. String becoming loose in physics means tension will become zero and then the bob will leave the circle. It will not be able to complete the loop. Okay, so let me try to give it that velocity, which is not very high and at the same time not very low. You saw that, right? So it went somewhere here and then it just left the circle. Now, before we continue, we need to know two concepts to understand this video nicely. And those two concepts are Newton's second law and conservation of mechanical energy. Let me quickly explain that. So imagine there is a body who has acceleration a this side. Now Newton said if you have acceleration a this side, there should be some net force in this direction. Net force. So this represents the total force on the body in this direction. And it says total force equals to mass of the body into acceleration of this body. Okay. So let's say there is a body, one force is here, let's say F1, another force is here, let's say F2. But let's say acceleration is this side. Then in this case, total force should be this side because wherever is total force, there will be acceleration. And since acceleration is here, total force should be here. That means this force should be greater than this force. So total force is what here? F1 minus F2. Minus because they are opposite to each other, right? This will try to cancel this. So total force is F1 minus F2. That will be m into E. So this is how we write Newton's second law. Of course, sometimes what happens, body has acceleration a this side, but force may be in this direction. So in that case, what we have to do is take the angle theta here and find the components of this f. One component will be f cos theta. One component here will be f sin theta. So since acceleration is this side, clearly this force will be balanced by some other force. We are not interested right now. So this force is balanced by some other force, maybe gravity or something. Okay, so this force will cancel this force and this acceleration this side will be provided by not this f this time, it will be provided by this component. So always remember you have to find the total force in the direction of acceleration. And in this example, the total force in this direction is f cos theta. So f cos theta will be m into A. Okay. And you should also know that if only conservative forces are doing work on a system, then the mechanical energy of the system remains conserved. That means kinetic energy plus potential energy at some initial point should be equal to kinetic energy plus potential energy at some final point. So you can choose any two points of the path of the body. As the body moves, you can choose two positions, initial, final, and you can apply this relation between those two positions. Kinetic and potential energy at initial position should be equal to kinetic energy plus potential energy at final position, provided only conservative forces do work. So no frictional forces should be there, no external agent should do pushing and pulling. Okay, so only conservative forces should do work, other forces should not do work. And conservative forces in your class 11 is gravity and spring force. As you come in class 12, we also learned that electrostatic force is also conservative force. So remember, if only conservative forces are doing work, we can use this formula. If friction is there, if some external agent Pankaj sir is pushing and doing some work, then we cannot use this formula. Then we have to go for work energy theorem. Okay. Now, for the sake of understanding, I have taken case 2 first. Okay. So in case 2, you remember, right? There was a rod whose mass is negligible, and here is a body whose mass is m. Remember, this end is fixed. Now, we have to find the minimum velocity of this u so that it completes the circle. Now, you know that if this velocity is very less, it will stop somewhere here and come back, isn't it? So, it is important that in order for this body to complete the loop, it must reach the highest point with some velocity, isn't it? It must reach the highest point with some velocity. Otherwise, what will happen? If it stops somewhere here, it will just come back, isn't it? If it stops here, it will come back. If it stops here, it will come back. So it is important that in order for this body to complete the circle, it must reach here with some velocity, some minimum velocity. So let us connect this velocity with this velocity. How do I connect that? Let's call this A, let's call this B. Now from A to B, we can use conservation of mechanical energy. So kinetic energy at A plus potential energy at A must be equal to kinetic energy at B plus potential energy at B. Now kinetic energy at A is half m initial velocity square, right? Potential energy, to write, we need to define our height 0. One of the ways is to take the lowermost point as height 0. So if I choose this point as height 0 in this problem, then potential energy at that point will be mgh, but h is 0, so potential energy will be 0. Kinetic energy here will be half mv square, and potential energy here will be what? Mg into height. Now if the radius of this circle is r, which is length of this rod also, then the height will be r plus r, 2r, right? The total height of this body from this reference line, height 0 line, will be 2r. M's will cancel everywhere. This is anyway 0, right? So you can remove this. So it is u square by 2 equals v square by 2 plus 2gr. If you multiply with 2 both the sides, you will get u square equals to v square plus 4gr, isn't it? And therefore your v square will be equals to u square minus 4gr. Let's call this equation 1. Now, to complete the loop, what is important? To complete the loop, I told you our body must at least reach highest point with some velocity, meaning this v should be greater or at least equal to 0. Better make it greater than 0, then only it will complete the loop. So if velocity is greater than 0, v should be greater than 0 means v square also should be greater than 0, right? And if v square is greater than 0, you can substitute v square here. What will you get? U square minus 4gr should be greater than 0. So if you take minus 4gr this side, you will get u square should be greater than 4gr. So u should be greater than square root of 4gr. So if I give initial velocity here more than root of 4gr, then it will complete the loop. So what is the minimum velocity that I must give? So the minimum velocity of u that must be given is minimum is root 4gr. It should be actually more than this, but in the limit we can say this is the minimum, right? For example, let us say this number is 2. That means you must give velocity more than 2. Now more than 2 is what? 2.000000 up to Mysore 0 you can write and then put 1. So this is also more than 2. So if I give velocity here this much, then it will complete the loop. But approximately this is what? 2 meter per second, right? So 2 meter per second is the minimum velocity that must be given so that it completes the loop. In this case, the answer is root of 4gr, where r is the length of this rod, or you can say radius of the circle in which the bob will move. Now let us discuss the second case, which was the case of the string. And why can't we say the same answer here? Because here also this should complete the vertical loop. So it should not stop somewhere here, otherwise it will come back, isn't it? So here also we could have told the answer is root 4gr the same way. Then why are we doing it separately? Well, the reason for this is, in the first case, remember we had a rod, and in rod, if you pull like this, it will sustain it by exerting tension forces. So when you pull like this, there will be tension forces when you pull, and even when you push, when you try to compress it, even then this will sustain. There will be tension forces. In other words, tension here will never become zero. So in the case of rod, whether you pull or you push, there will be tension forces developed in the rod. Whereas in the case of string, something like this, if you pull, there will be tension force, but if you push, there will be no tension force, right? The tension here will become zero. And therefore, this case is not exactly same as the previous case. I will show you that if you give, let's say here also the same velocity as in the previous case, which was 4gr. Suppose you give slightly more than this velocity, slightly more. Then you may think like in the previous case, it will complete the loop, right? Well, yes, if it was able to reach till here, it will have some velocity and therefore it will complete the loop. But the problem is, I will show you that when you give this much velocity, our pendulum will reach somewhere here, and when it reaches somewhere here, the tension in this string will become zero. And tension becoming zero, in other words, means the string will become loose, and thereafter it will not be able to go in this circle, because now there is no longer tension. So the only force is gravity, and if you have some initial velocity and the only force is gravity, you will follow a parabolic path. So our pendulum will not complete the circle if you give velocity equal to this much. In fact, what will happen? It will reach somewhere here and the string will become loose. So when our string is somewhere here, there is a chance that tension may be zero. So we need to check that no matter what, at any point, tension is not zero. If tension anywhere becomes zero, then our string will become loose and the body will leave the circular path. So it will not complete the circle. So we need to check the tension at no point is zero. Okay. So let's say our body has reached here, and let's say here we try to calculate the tension. So you can see here one tension force will be T along the string away from the body, right? That's how we draw tension force. And here gravitational force mg. We know from previous topic that when something is going in a circular motion, there will be a acceleration towards the center, and that acceleration is called centripetal acceleration, right? So there will be an acceleration towards the center called centripetal acceleration. AC I have used, okay, the symbol AC. So now if you try to check what force is providing this acceleration, then I need to take components of mg, because tension is already in the direction of acceleration, right? So let us take components of mg. So one component here, one component here. If this is theta, this is also theta. So this is mg cos theta. and obviously this will be mg sine theta. So now if you ask what is the total force in the direction of this acceleration, then we can write from Newton's law, total force in this radial direction is equals to mass into acceleration in this radial direction. So remember, whenever you write Newton's law, we are writing it for one particular direction. So this is along radius. So what is the total force this side? Tension minus mg cos theta. Why minus mg cos theta? Because mg cos theta is in opposite direction to tension, right? So total force this side is tension minus mg cos theta, which should be equal to m into acceleration towards center, which is centripetal, and the formula for that is v square by radius. V, remember, not here. This velocity we have used u. So here the velocity is, let's say, v. So from here tension becomes equals to mv square by r plus mg cos theta. Now very interesting, you have to note here that there is cos theta in this formula for tension. Let me now use this equation to explain to you why tension can become zero at some point on this path during its motion for a string. So how tension can become zero, or why tension becomes zero? Let's try to understand. So initially when the pendulum was here, the angle made was 0, right? So theta was 0. And if theta is 0, what will be this cos theta? That will be 1. And as theta increases and reaches, let's say, here, up to here, so in this quadrant, theta goes from 0 to 90. So when theta is 90 degree, which means our pendulum has reached here, right? This is the angle 90 degree, right? So when our pendulum is here, theta will be 90 degree. So that time what will be cos theta? Cos 90 is 0. That means this became from 1 to 0, so it decreased. So since cos theta decreased, tension also decreased. But still, between 0 degree to 90 degree, you can see cos theta is positive. And cos theta positive means this is positive and this is already positive, v square is positive. So tension is positive in this part. Tension positive means what? The string is tight. So in this part, our tension in the string will never be zero because it is always positive. But the moment our pendulum crosses this position and reaches here, you can see our theta becomes obtuse. So let us say as theta approaches 180 degree means as our pendulum reaches here. What is cos theta now when theta becomes 180? Minus 1. So that means now between this angle 90 degree to 180, which means from here to here, our cos is negative, right? From 90 degree to 180 degree, our cos is negative. And that means this term became negative and this term is positive. So do you see that there is a possibility that this and this may add and give you 0. And that's why there is a chance that tension somewhere here may become 0. Okay? So you must understand that as our pendulum moves, this theta keeps changing, and as theta changes, cos theta changes, and as cos theta changes, tension changes, right? And when is cos theta maximum? When it becomes 1. So when cos theta is 1, tension will be maximum, and when cos theta is minus 1, which is the minimum value of cos theta, tension will be also minimum. So when cos theta is 1, tension is maximum, and that happens at what angle? 0 degree, right? Cos is 1 for 0 degree. 0 degree means here. So tension is maximum here. And when it is minimum, when cos theta becomes minus 1. And cos theta minus 1 means tension is minimum, and which happens at theta equals to 180 degree. And 180 degree means at this point, right? the highest point. So at the lowest point, tension is maximum. At the highest point, tension is minimum. Now remember, our aim was to find out the minimum velocity that we should give here, the minimum value of this velocity, so that our pendulum can complete the loop, right? So now we understood that as it keeps moving, tension decreases here till here it becomes minimum, and then again tension increases, right? So here tension is minimum, right? Now we don't want this tension to become zero. Now if you don't want tension to become zero, then it is important that minimum tension itself is greater than zero. That way you will be sure that tension nowhere is zero, isn't it? Think about this once. Suppose I say everybody should get marks more than zero. If everybody should get marks more than zero, then the minimum marks in the class, if that is greater than zero, then I know everybody got more than zero, isn't it? So if the minimum tension itself is greater than zero, then obviously other tensions will also be greater than zero, because the minimum is greater than zero, right? So if let's say tension is 2, 5, 8, 10. So which is the minimum tension? 2. So if this is greater than 0, all others will be also greater than 0. And if tension is greater than 0 all the time, it means the string will never be loose, right? So the condition that it completes the loop is the minimum tension, which is here, should be greater than 0, right? Let's call this equation 1. At which point tension becomes minimum? Highest point, right? And to find the minimum tension, to find tension, we have to always make use of Newton's law. So here tension is minimum. So let me call it T minimum along the string away from the body. And one more force is what? mg. And you know there is a centripetal acceleration towards the center. And this acceleration should be provided by force towards the center, right? And what is the force towards the center? Again, use Newton's law. Net force in this radial direction is mass into acceleration in this radial direction. Net force in this direction is what in this case? T minimum plus mg, and acceleration in this direction is v square by r. What is v square? Velocity here. But remember, our aim was to find this velocity, right? So how to connect this velocity with this velocity? Whenever you want to connect two velocities, always use conservation of energy. Okay. So from here to here, let me use kinetic energy plus potential energy at A should be kinetic energy plus potential energy at B. Right? Total energy should be conserved. Of course, this is mechanical energy because there is no loss of energy anywhere, because this tension, if you look carefully, it acts in this radial direction. Right? Tension always acts in this radial direction, and displacement is in this velocity direction. So your instantaneous velocity, which means displacement, small displacement here, and tension are perpendicular. So tension is not doing any work, right? And there is no air resistance in this problem. So kinetic energy here plus potential energy here should be equal to kinetic energy here plus potential energy here, because the only forces here which are doing work is gravitational force, and you must know gravitational force is a conservative force. And when conservative forces act, please remember, we can use conservation of mechanical energy. So kinetic energy here is how much? Half mu square. Potential energy here, let me take 0. Kinetic energy here will be half mv square. We did this part before, right? And potential energy here will be plus mg, height is 2r. So m gets cancelled. You can multiply with 2 both sides. So this half will cancel and this 2 will become 4. So v square will be, this 4gr will come here, u square minus 4gr. So you can substitute for this v square in this equation. So let us substitute this v square in this equation. What will you get? Tension minimum plus mg is equals to m into, what is v square? U square minus 4gr divided by r. Right? Okay. We can try to simplify this. So tension minimum plus mg will be, let's open the bracket, mu square by r minus m into 4g, right? This r and this r will cancel. So now from here tension minimum will be how much? Mu square by r minus 4 mg, and this mg will go that side, minus mg minus 4 mg minus 5 mg. So this is the minimum tension when you give initial velocity u, remember here. So now we know already to complete the loop, this is the condition, right? To complete the loop in case of string. Because in case of string, remember, tension can become 0. And we have to make sure that tension is nowhere 0. And if tension nowhere should be 0, minimum tension should be greater than 0. And minimum tension is at the highest point. And what is the minimum tension? Mu square by r minus 5 mg. So this should be greater than 0. You can take minus 5 mg this side. So mu square by r is greater than 5 mg. Cancels, so u square becomes greater than 5gr, cross multiply r, right? Cross multiply this r, so u will be greater than 5gr, square root of 5gr. So in order to complete the loop, what is the condition now? The initial velocity here should be greater than, not root 4gr like previous case, it should be greater than root 5gr. So please remember this, okay? So we learned that in order to complete the loop, the velocity given here should be greater than root of 5gr. Let's say I give an initial velocity of root of 4gr. Then will it complete the loop? No, because you need more than root 5. This is root 4. So it will not complete the loop in the case of string. The reason is, again I told you, somewhere here when it reaches, it will have velocity, but tension will become 0 somewhere. So let's try to find the angle at which the string will become loose. So if tension here is 0, then at what position it is 0 we need to find. So let's say this angle is alpha. Then the total angle from this initial will be 90 plus alpha, right? This is 90 and this is alpha. So total angle turned will be 90 plus alpha. When it is here, tension is 0, so the only force here will be mg. So one component will be here, one component will be here. So you can check if this is alpha, this is 90. So this will be 90 minus alpha, right? And therefore this component of mg towards the center will be mg cos 90 minus alpha, which is mg sin alpha. Cos 90 minus alpha is sin alpha. So the force towards the center, again I will apply Newton's second law in the radial direction. So total force towards the center is m into a. What is the total force towards the center this time? Mg cos 90 minus alpha, which is mg sin alpha. And centripetal acceleration here is what? V square by radius. M gets cancelled. So now we have to find this, because we have two unknown. Alpha is what we are trying to find, because we want to know the position of this string at which the tension here becomes 0. So we want to know this angle. So V is also unknown, alpha is also unknown. So we need one more equation. How to get one more equation? By now you must have understood that either you can use Newton's second law or you can use conservation of mechanical energy. So between this point and this point, let us apply conservation of mechanical energy. So kinetic energy at A plus potential energy at A should be kinetic energy at B plus potential energy at B. Kinetic energy at A will be what? Half m u square. Square of this will be 4gr. Potential energy at A is 0 because I will choose this height as 0 height. We can choose height 0 anywhere we want, right? Kinetic energy at B here, that is half m v square. Now potential energy here, how to find? So to find the height of this point, I have cleared the previous diagram. So this angle was alpha, right? So this height will be how much? Well, this radius is r, this is alpha, so this opposite side will be r sin alpha, right? So in a right angle triangle, if this angle is alpha, this is r, then this will be what? Sine alpha will be opposite side by hypotenuse side. So if you cross multiply opposite side, this is opposite side, will be cross multiply r sine alpha. So opposite side is r sine alpha, and this height plus this height will be the total height from the ground, not ground, for total height from the initial point. So what is the total height? This is r radius and this is r sine alpha. So total height will be, so potential energy will be mg, total height is r plus r sine alpha. Right? So now let's try to simplify this. First m you can cancel, and this denominator 2 you can cancel by multiplying with 2. So 4gr is equals to multiply with 2 v square multiply with 2 2gr you take common 1 plus sine alpha. Now this is straightforward to solve. So 4gr is equals to v square plus 2gr plus 2gr sine alpha. So now if you bring this 2gr this side, 4gr minus 2gr will be 2gr is equals to v square plus 2gr sine alpha. This is your equation 2. So now you have to solve this equation in the first equation. First equation, if you check your notes, was g sine alpha is equals to v square by r. These two v are obviously same, final velocity, right? So from here what will be v square? gr sine alpha. So let's substitute, this was your equation 1. So let us substitute for v square from equation 1 in equation 2. So remember, one equation comes from Newton's law, one equation comes from conservation of energy, right? That's it. So if we solve this, what will you get? 2gr is equals to v square. V square is gr sine alpha plus 2gr sine alpha. And that means your gr cancel. So 2 equals to 3 sine alpha. So sine alpha equals to 2 by 3. Okay. So we found at what angle alpha will tension become 0? When sine alpha is 2 by 3, which means alpha will be sine inverse 2 by 3. Now they may ask you to find the total angle turned by the string or the pendulum by the time tension becomes 0. So this total angle theta is not alpha, right? It is this angle 90 plus alpha. But we know sine alpha. So what we will do? We will take cos both sides. I hope you understood, because if you take cos both sides, then cos 90 plus alpha is minus sine alpha, right? Cos is in 90 plus alpha is second quadrant, so cos will be negative. And sine alpha is how much we found? Sine alpha is 2 by 3. So theta, the angle turned, will be what? Cos inverse minus 2 by 3. So when the pendulum turns by an angle of cos inverse minus 2 by 3, tension will become 0. Okay.